Welcome to today's paper reading. Today's paper is titled, A Survey of Resource-Efficient LLM and Multimodal Foundation Models. This paper was published on the AR14 preprint by Mengwei Su and colleagues from Beijing University of Posts and Telecommunications, Peking University, and Tsinghua University. The abstract introduces a scalable mobile AI foundation model that unifies diverse AI tasks by employing multimodal embeddings and a transformer-based backbone for understanding and reasoning across inputs such as text, images, audio, and motion data. This approach enhances efficiency and scalability for mobile AI. The model also includes a cost analysis focusing on the multi-encoder module, decoder module, and resource-efficient architectures. Figure 1 illustrates the stark contrast in electricity consumption between AI operations and typical country usage. The data, sourced from 81, highlights that by 2027, NVIDIA is projected to ship 1.5 million AI server units annually, which would consume at least 85.4 terawatt-hours of electricity. This amount surpasses the annual electricity usage of countries like New Zealand and Austria. Additionally, the figure notes Google's electricity consumption in 2022, emphasizing the significant energy demands of AI technologies. Figure 2 provides a structured overview of the survey's organization, categorizing the content into sections on large language models, LLM, multimodal foundation models, vision foundation models, and language foundation models. It highlights various resource-efficient techniques, including algorithmic improvements, architectural innovations, and system-level optimizations. Key methods for enhancing efficiency are detailed, such as efficient attention mechanisms, dynamic neural networks, and diffusion-specific optimizations. Figure 3 illustrates the evolutionary trace of foundation models, highlighting the development from text-based to multimodal models. The figure shows the transformer architecture, which uses attention mechanisms to process sequences. It also depicts the encoder-decoder structure, which is fundamental for tasks like text generation and translation. The evolution includes advancements in model size and complexity, moving from language models to those that can process images and audio. Table 1 provides a comprehensive overview of milestone language foundation models and their typical tasks. It highlights key models such as BERT, DistilBERT, Roberta, and SentenceBERT, which are encoder-only models designed for various text classification and similarity tasks. The table also covers encoder-decoder models like T5 and BART, which are used for text-to-text tasks and denoising autoencoding, respectively. Additionally, it features decoder-only models including GPT-1, GPT-2, and GPT-3, which are known for their capabilities in text generation and unsupervised learning. Other notable models listed are GLM, InstructGPT, PaLM, and Llama, each with unique features and applications in natural language understanding and generation. Figure 4 illustrates the weight storage and flops, floating point operations, cost of various language foundation models, FMs. The embedding component accounts for approximately 25% of the total storage costs, but incurs minimal computational costs during inference due to its lookup table nature. The feed-forward network, FFN, layer is the most computationally intensive part, primarily because it consists of two fully connected layers. The language model head, LM head, varies in form depending on the task. For example, it is a classification layer with a softmax function for discriminative tasks like BERT, and a linear layer for generative tasks like GPT/T5. The size of the LM head is directly proportional to the vocabulary size. Figure 5 illustrates the inference flops of GPT-2 under varying token lengths. The attention mechanism's quadratic complexity significantly increases computational demand with longer sequences. The feed-forward network, FFN, scales linearly with input length but quadratically with model dimension. The implementation of a KV cache mitigates computational costs by reusing key and value vectors, though it increases memory requirements. Table 2 presents a comprehensive overview of milestone vision foundation models, FMs, and their typical tasks. The table lists models such as DTR, ImageGPT, Vision Transformer, ViT, DATI, SegFormer, YOLOS, Swin Transformer, ViTMAE, ViTs by DINOV2 and LVM, detailing their architectures, oriented tasks, parameters, pre-training methods, pre-training datasets, and testing datasets. Key tasks include object detection, instance segmentation, panoptic segmentation, image classification, semantic segmentation, and video action classification. Pre-training methods range from supervised and self-supervised to distilled, highlighting the diversity and evolution in vision FMs. Table 3 presents a comprehensive overview of milestone multimodal foundation models, FMs, and their typical tasks. Key models include Daliang, which boasts 12 billion parameters and specializes in cross-modal generation tasks. Qipeng, with parameters ranging from 400 million to 1.6 billion, also focuses on cross-modal generation. Stable Diffusion, with 1.45 billion parameters, is renowned for its capabilities in image synthesis. These models represent significant advancements in the field of multimodal AI, demonstrating the integration of various modalities and their applications across different tasks. Figure 6 provides a detailed cost analysis of various modules within multimodal foundation models, FMs. It highlights the resource requirements of the image encoder, which has 0.63 billion parameters and occupies 2.4 gigabytes of memory. The large FMs module, exemplified by Vicuna 7b, significantly exceeds these requirements with 7 billion parameters and 14 gigabytes of memory. Additionally, the diffusion module, represented by Stable Diffusion 2.1, includes components like the UNet VAE and Qipeng model, each contributing to the overall cost. Figure 7 illustrates the parameters and flops of various modules within Stable Diffusion 2.1. The UNet, responsible for denoising, has 865 million parameters and 759 billion flops per sample. The VE, handling image encoding and decoding, has 83 million parameters and 4 trillion flops per sample. The Qipeng model, used for text encoding, has 289 million parameters and 289 million flops per token. Figure 8 provides a visual overview of resource-efficient architectures, focusing on reducing computational and memory expenses in large FMs. It categorizes these architectures into efficient attention mechanisms, dynamic neural network strategies, and diffusion-specific optimizations. The figure highlights the core blocks and conventional taxonomy of large FMs, aiming to minimize resource consumption. Table 4 provides a detailed comparative analysis of the time and space complexity among various transformer models and their variants. The table highlights the computational efficiency of different architectures, with T denoting the sequence length and D representing the hidden dimension. This analysis is crucial for understanding the performance trade-offs in transformer-based models, especially in scenarios involving long sequences and high-dimensional data. Figure 9 provides a visual summary of various efficient attention architectures. It categorizes these architectures into 4 main types: self-attention, sparse attention, approximate attention, and attention-free. The figure highlights specific models such as linear transformers, RetNet, and RWKV, which are known for their complexity reduction methods. Additionally, it outlines the time and space complexity for each type, including O t to the power of 2d, O t log td, and O td, providing a clear comparison of their efficiency. Figure 10 provides an overview of traditional and dynamic transformer architectures. It highlights the traditional transformer structure, which forms the basis for many modern models. The MOE version transformer is depicted with sparse parameters, illustrating its efficiency in handling large models. Lastly, the early exiting transformer is shown, which dynamically adjusts its computational process based on confidence levels, enhancing both efficiency and performance. Figure 11 provides a summary of various resource-efficient vision transformer (ViT) variants. Levitt is highlighted as a hybrid neural network designed for efficient image classification, utilizing an increased number of convolutional layers for embedding. Mobile ViT is presented as a lightweight transformer architecture that employs CNNs to construct a more efficient model, tailored for practical hardware platforms. Efficient Former is introduced as a lightweight CNN transformer hybrid architecture, achieving efficient on-device inference with minimal latency. Figure 12 provides a comprehensive overview of various resource-efficient algorithms used in the pre-training and fine-tuning of large foundation models, FMs. The figure categorizes these algorithms into several key areas: training data reduction, neural architecture search, progressive learning, and mixed precision training. Training data reduction techniques focus on eliminating redundancy in datasets through methods like deduplicating text datasets and removing image patches. Neural architecture search methods, such as zero-shot NAS and elastic ViT, automate the design of efficient model architectures. Progressive learning strategies, exemplified by stacking BERT and compound GROW, start with smaller models and gradually increase their size, reusing computations from previous stages to optimize resource usage. Mixed precision training, often utilizing half-precision floating-point data representation, significantly reduces memory requirements and speeds up training processes. Figure 13 provides a comprehensive summary of various fine-tuning algorithms used to adapt pre-trained foundation models to downstream tasks efficiently. The figure categorizes these techniques into additive tuning, selective tuning, and reparameter tuning. Additive tuning includes methods like adapter tuning, prompt tuning, and prefix tuning, which introduce additional parameters or modify input prompts to reduce the need for full model retraining. Selective tuning focuses on freezing most parameters and selectively updating only a small portion, enhancing efficiency through techniques like layer freezing and dynamic sparse tuning. Reparameter tuning targets a smaller subspace for adaptation, often using low-rank adapters and quantization techniques to maintain performance while significantly reducing training costs. Figure 14 illustrates the low-rank adaptation, LoRa, method and its various optimization strategies. LoRa significantly reduces the number of trainable parameters by freezing the pre-trained weight matrix and fine-tuning low-rank matrices A and B, which can have ranks as low as 2. This approach decreases the amount of gradient values required for storage during training. However, LoRa still exhibits performance gaps compared to full fine-tuning. To address this, various optimization methods have been developed, mainly categorized into 3 strategies: adding trainable parameters, improving initialization, and optimizing the learning procedure. Delta LoRa aims to bridge the performance gap by updating the pre-trained weights through the product of low-rank matrices A and B, thus adding trainable parameters without incurring additional memory overhead. PySSA identifies an issue where LoRa initializes low-rank matrices with Gaussian random values and zeros, resulting in very small initial gradient values and slow convergence. PySSA proposes using singular value decomposition, SVD, on the pre-trained weight matrix, freezing the matrix with smaller singular values as a residual matrix, and initializing the trainable low-rank matrices A and B with the largest singular values. This optimized initialization method yields faster convergence and improved performance. Lastly, DORA focuses on enhancing the learning process itself to further improve efficiency and effectiveness. DORA observes that LoRa and full fine-tuning exhibit different update patterns. Therefore, it decomposes the pre-trained weights into their magnitude and directional components, and fine-tunes the directional matrix. This brings the update pattern closer to that of full fine-tuning, leading to better training outcomes. Figure 15 illustrates the various model compression techniques applied to large language models, LLMs. These techniques are categorized into 4 main areas: pruning, knowledge distillation, quantization, and low-rank decomposition. Pruning methods include both structured and unstructured approaches, which aim to remove redundant or non-essential parts of the model to reduce size and computational costs. Knowledge distillation involves transferring knowledge from a complex teacher model to a simpler student model. Quantization techniques focus on converting high-precision weights and activations into lower bit representations, which can be further divided into weight-only quantization and weight activation co-quantization. Low-rank decomposition approximates weight matrices with smaller matrices to reduce the number of parameters and computational overhead. These compression methods collectively aim to enhance the efficiency and scalability of LLMs without significantly compromising their performance. Figure 16 provides an overview of resource-efficient systems, focusing on distributed training resilience, parallelism strategies, and inference accelerating techniques. It highlights various methods for optimizing distributed training systems, including resilience through checkpoints and redundant computations, parallelism through data, model, and sequence parallelism, and communication optimizations. Additionally, it covers memory optimizations and heterogeneous GPU training. The figure also outlines inference accelerating methods, such as kernel optimization, request batching, and scheduling, as well as memory-saving techniques and emerging deployment platforms for efficient large language model serving. Table 5 provides a comprehensive summary of widely used open-source frameworks for training and deploying large foundation models, FMs. Key frameworks include DeepSpeed, Megatron LM, ALPA, FlexFlow, and Colossal AI for training, and Hugging Face PFD, OpenLLM, DeepSpeed MI, and VLLM for inference. Additionally, federated learning frameworks such as Flower, FedML, FATE, and Federated Scope LLM are highlighted for their role in ensuring data privacy while training large FMs. This introduction section highlights key techniques for making large language models, LLMs, and multimodal foundation models more resource efficient. Firstly, quantization techniques such as hardware-friendly outlier victim pair quantization and low-rank approximation are discussed. These methods aim to reduce the computational and memory footprint of models without significantly compromising performance. Secondly, the section covers inference optimization strategies, including turbocharging NLP inference at the edge and faster inference on GPUs, which are crucial for deploying models in resource-constrained environments. Lastly, federated learning approaches are introduced, which enable collaborative model training across decentralized data sources, exemplified by applications in mobile keyboard prediction and efficient prompt tuning in federated settings. In this section, we explore various training approaches that enhance the efficiency of large language models, LLMs, and multimodal foundation models. Techniques such as patch dropout for vision transformers, cache gen for KV cache compression, and token mixing for video language models are highlighted. We also discuss efficient architectures like Swin Transformer, Mobile ViT, and Dynamic ViT, which optimize model performance for resource-constrained environments. Additionally, we cover inference optimization strategies including LLM-QET, SpinQuant, and SpecInfer, which aim to reduce computational overhead and improve model serving efficiency. In this experimental setup, the authors utilized data parallelism and have published their findings as an AR14 preprint in 2023. The research team includes Yilong Zhao, Qianyu Lin, and Ken Zhu, among others. Their key contribution is the development of the Atom framework, which focuses on low-bit quantization for efficient computing. In the related work section, the authors discussed the importance of efficient large language model, LLM, serving. They referenced the work of Lianmin Jing et al., who developed ALPA, a system that automates inter- and intra-operator parallelism for distributed deep learning. This work was presented at the 16th Usenix Symposium on Operating Systems Design and Implementation in 2022. The authors also highlight the need for efficient LLM serving, focusing on the contributions made by Jing et al. In this area. These contributions include the automation of parallelism in distributed systems and the enhancement of operational efficiency in serving LLMs. In this conclusion, the focus is on programming large language models using SGLang, as detailed in the AR14 preprint AR14, 2312.07104, published in 2023. The paper by Wang Chen Zhao et al. Introduces early exit techniques for fast and robust inference, published in Advances in Neural Information Processing Systems in 2020. Additionally, Bin Zhu et al. Contribute to robust inference methods, with their work involving Nianan Ning, Yan Yan, and Jiaxi Siyu, also published in 2020. Thank you for watching.